And good afternoon for the audience and for everybody. My name is, as Emre told, Gábor Drotos. Drotos, in fact. I work in Palma de Mallorca with my postdoc supervisor Cristóbal López there and two other colleagues with whom this is a joint work. In particular, Rebecca de la Fuente was interested in the vertical distribution of some special particles in the sea, in the Mediterranean Sea. And for that, she carried out some dispersion simulations for first understanding. And further simulations were planned, but unfortunately, we only have the Mediterranean setup so far. So what kind of particles was Rebecca interested in? They were microplastic particles, how they sink and how they distribute within the water column. That was the question that she asked, and it turned out that the easiest part is to investigate negatively buoyant rigid microplastic particles. But our modeling framework also applies to marine biogenic particles, and we believe that our results, even though not quantitatively perfect for a true realistic estimation, they will give insight to many phenomena that are qualitatively very much relevant for the real world. So our modeling framework depends on a very simple equation of motion. In this, the velocity of the particle of the particles of interest is simply a sum of the fluid velocity field and the settling term. And the settling term is what contains all the parameters of the problem, including the densities of the fluid and the particle radius, and other relevant quantities. But as you can see, this is the only parameter that appears in the equation of motion. And to have a realistic setup, we choose three different sinking velocities, settling velocities, of which the smallest one is available only for a partial simulation, simulation of partial length, but I will speak more about the other two. And the other thing to specify here in the equation of motion is the velocity field, which is a simulated velocity field from the Mediterranean, based on a rather large scale, but realistic model. And finally, the initial conditions of the particles were distributed uniformly over the whole Mediterranean in a near surface plane. And from that near surface plane, these particles were let sink, and Rebecca followed the time evolution of the positions of these particles. What did she find? First of all, I would comment on the horizontal displacements. At the very most, these particles were displaced by a few hundred kilometers, which might not be negligible, but this is small compared to the basin size and relatively small compared to the relevant features of the flow. I will return to this point. We just remember this at the moment. And then I will directly present the results related to our main question about the vertical dispersion. We represent vertical dispersion in terms of the variance of the vertical coordinate taken over all of the particles of the simulation, of the whole, initializing the whole Mediterranean. And here it is plotted as a function of time for the highest settling velocity used. And as you can see, it is very far from trivial. First of all, at the beginning, we have a super diffusive regime with an exponent larger than 2, which we explain by the presence of an autocorrelation in the velocity field. Then it is not a surprise to find some normal diffusion as a result of fluctuations or some kind of turbulence or some noise, if you want, or chaos. Anyway, something irregular that produces normal diffusion. What is more surprising is a ballistic regime after this normal diffusive regime. And to explain that, Emilio Hernandez Garcia, one of the collaborators, came up with a model in which the position, vertical position of particle I is the sum of 3 terms. First of all, we take the average vertical position of all the particles that we have, and then we introduce the result of a Wiener process which explains the fluctuations. But we also have a third term here. This third term corresponds to a bias or a drift experienced by particle I, which is related to some persistent up or down welling in the velocity field. For short times, we can take the simple average velocity experienced up to the particular time instant. That would be omega I, but this omega I bar represents a long-term representation when this Wiener process is already filtered out. And we assume that at the position of particle I, this is a well-defined quantity different from 0. Note that it assumes restricted horizontal mixing. Because if all particles were mixed all over the Mediterranean at each time step, each particle would be equivalent, and then this quantity would obviously be 0, because the average motion of all the particles would follow the average motion of all particles. Okay, so let us assume so far that this is a useful approximation. And then if we assume furthermore that the two additive terms are uncorrelated over different particles, then the time evolution of the variance is the sum of a ballistic and a linear term. So when these two terms are equal, that approximately gives the transition between a normal diffusive and the ballistic regime, the time of this transition. Now, let us see in more detail what we can tell about this quantity appearing in a denominator, which is the variance of this drift term, the variance of this drift velocity taken with respect to all particles. Actually, this must represent a patchiness in the flow. If there were absolutely no horizontal dispersion, then it could be different for each particle, but we know that there is a little horizontal displacement. So in order to have a well-defined omega I bar, then we need that this drift contribution is the same within a reasonable neighborhood of the original particle position. And if I evaluate omega I at some sufficiently late time, then we can see that and plot it as a function of the initial position, initial horizontal position, we can see that it indeed exhibits a patchiness all over the Mediterranean. So, but it is also not completely homogeneous. There are considerable deviations, but in a patchy way. Then we can evaluate these two quantities, predicting the time of the transition. First of all, the diffusion constant can be estimated by a linear fit to the variance as a function of time in the normal diffusive regime, just what I showed a few slides before. And then for this variance of the drift contribution, we can just evaluate this omega I as some sufficiently late time with respect to all the particles as seen in our simulation. So basically take the variance with respect to this plot on this particular slide. And then the estimation that we obtain perfectly separates the normal diffusive and the ballistic regimes. And we regard this as a confirmation of the validity of Emilio's model and a confirmation of the patchiness as the root cause of patchy upwelling and downwelling pattern as the root cause of the appearance of this ballistic regime. So we believe that we do understand this ballistic regime, and we do not take very much care of this bottom stop of the dispersion, where we believe that water simply stops moving, and it is anyway very much restricted to the vicinity of the seafloor, so we don't take very much care of that. What we take more care of will be seen from the next simulation with this medium value of the settling velocity. After the initial superdiffusion, a more complicated structure of the autocorrelation function results in a regime of subdiffusion, which is followed by the normal diffusion. We think that ballistic dispersion is indeed observed for a long time, short time after the normal regime, and we base our guess on our estimate for the transition time, which approximately agrees with this true observed transition between these two regimes. But it is quite obvious that for even longer times, we return to normal diffusion, which corresponds to horizontal mixing in the flow. When particles at this settling velocity move farther away from the initial position, this will reduce the variations, the spatial variability in this drift term. Actually, this drift term will not be constant anymore and will approach zero. And in that case, we must return to normal diffusion if we have fluctuations. Okay, if I plot the same variance as a function of depth, we can also learn that the first transition from the superdiffusive to the normal diffusive regime takes place around 100 meters depth, irrespective of the choice of the velocity, of the settling velocity. And it turns out to be true in the shorter simulation as well. So we regard this as an indication for organization of our results according to depth, actually to the determination of this first transition from this autocorrelated regime to the normal diffusive regime by switching between different physical regimes, spatial regimes in the flow, which are reasonable to be present above and below 100 meters. And this also, for example, above 100 meters, we basically have the mixed layer. And this also points out the importance of the evaluation of the relevant evaluation of autocorrelations in our problem, which should be performed in a Lagrangian sense. So I would arrive by this to our conclusions. First of all, we can observe some really non-trivial dispersive phenomena when investigating the vertical dispersion of sinking particles, sinking idealized particles. Then we also learn that for a proper investigation, we need to evaluate autocorrelation in Lagrangian sense, maybe not a surprise, but still something that seems to be important. What is more surprising is that by this investigation, we learn about the flow, how the flow is organized, both in vertical, in terms of some stratification, by which I mean here the presence of different flow regimes in different layers, like the mixed layer, so it is clearly seen. And also the importance of the patchiness of upwelling and downwelling. And the robust laws that we saw emerge also suggest a kind of a time independence. Of course, the flow on a small scale depends very much on time, but the details of this dependence is not important, seems to not be important for the qualitative phenomena that we found. And one further remark is that patchiness of the flow clearly indicates that for a given evaluation, for a targeted study, different regions must be modeled separately. And in that case, we will find different results in different regions of the sea. And it is here where I mentioned that this organization is obviously related to oceanic mesoscale eddies. And I just mentioned that from the dispersive phenomena, we also tried to construct the steady distribution, assuming continuous particle input. And because of the relatively narrow dispersion, we find it to be close to uniform with our parameters. But more detailed investigation is part of future work, and I would like to thank you for your attention.
Okay, thank you, Gabor, for this interesting talk, especially if you consider that it talks about the sinking of microplastics. I think it's one of the hot topics of today's seafood industry. Yeah, thank you. It was nice. Please, from the side of audience or also from the side of panelists, put your questions in the question and A window. Up to now, I don't see many questions, but maybe I can take advantage of this moment until maybe some of the audience write some questions. Okay, you mentioned the regional modeling is preferred at the end, but I didn't understand what you exactly refer to by saying regional modeling. It's regional in the sense, in the vertical sense, in the
no, in horizontal
surface. Okay, yeah. So
in horizontal. So if we want to understand how plastics, for example, are distributed within a given region, then we have to select that given region and perform simulations specifically for that region, and then it might yield very different results compared to some other region. This is what we think is one consequence of these differences in this vertical velocity in the flow structure.
Okay. Okay, we have a question from Johannes Osborne.
Mm-hmm.
Thank you for your talk. Could the model be extended to consider the effect of extreme weather events such as hurricanes? So some rather particular conditions if they are
Yeah,
present.
as you saw, the sinking time for these fastest sinking particles is around 20 or 30 days until all the particles reach the bottom, and the velocity field taken as a basis corresponds to some kind of usual conditions in the Mediterranean. Of course, in the Mediterranean, we don't have tropical cyclones, but of course, if we go to a real ocean, there we can have tropical cyclones. And actually, thank you for this question. It is a very good idea that during that time, the flow structure can be altered very much with respect to the usual one, and that may have very strong impact by perturbing the distribution of the sinking particles, for example, sinking microplastics. Yes, but this effect is simply has to be taken into account through the velocity field. So not our model, where I am. So not our model, but through the velocity field that we use as an input for our model.
Okay. I don't see any other questions. Then seeing that we have still 2-3 minutes more, I would like to again take advantage of the situation. Related to my first question, I asked that what was this regional modeling referring to? So I suppose depending on the region, you decide. I mean, you showed 3 possible values for the settling velocity in the model of your particle velocity, and I suppose these are okay. The first sub question, let's say. Based on what you decide, those 3 values for these settling velocities. Secondly, this settling velocity is the parameter which shows the differences between among different regions, right?
Yeah. Yeah. So first of all, these 3 settling velocities were chosen to correspond to different plastic densities, different physical densities of microplastic particles. Okay. Of course, the highest settling velocity corresponds to the heaviest microplastic particles, and the smallest one corresponds to those that are still sinking, are still negatively buoyant, but are closest to neutrally buoyant, and all of them may be relevant, or all of them are relevant for different materials. And yes, yeah, here is switching between the medium velocity and the highest settling velocity. Here we can see the alteration.
Yeah.
So we can see that besides a very different settling time, very different residence time, the main difference is different expression of the horizontal mixing, which is more important for a slower settling velocity. So of course, if we have a smaller settling velocity, particles are advected farther away in the horizontal, more horizontal mixing occurs. And then, as you pointed out, regional modeling may be less important. Taking a particular restricted region is less important than for fast sinking particles. Yeah.
Okay, okay.
Thank you for your question.
Thank you for your answer. Okay, I think, okay, I don't see any other questions, so maybe we can continue with the next talk. Thank you, Gabor, again for this nice